Hi all, let's see the next topic of Unit 3, Multiplication of a Booth's Algorithm, Part 2. In today's lecture, we are going to discuss an example problem on Booth's algorithm which is used to multiply 2's complement data. So in the previous lecture, we have already discussed the flowchart of a Booth's algorithm. Let me give you a recap. So the flowchart mainly consists of the input two operands where the first operand is said to be called as your multiplicand and the second is your multiplier. The multiplicand is stored in a register BR, whereas your multiplier it is stored in a register QR. And the next step of your algorithm is the initialization of your register. So we have a register, a temporary register AC, which is initialized at all zeros at the starting of your algorithm. And the sequence counter, which is initialized to the value n, where n represents the number of bits of your multiplier. And Qn plus 1 is initialized to 0. Next, coming to the next step, we are going to check the values of Qn and Qn plus 1. So Qn plus 1 is an extra flip-flop. It is initialized to a value 0 and Qn is nothing but the LSB bit of your multiplier. So these two bits are checked and based on the value output of these two bits, we are going to decide what is the operation that we are going to perform on the multiplicand and the multiplier. So when if Qn and Qn plus 1 bits are a combination of 1, 0, then you are going to subtract the contents of AC register and BR register. It is done by means of AC plus BR complement plus 1. Minus BR can be represented as a 2's complement form, which is called as BR complement plus 1. And after performing a subtraction operation on the contents of these two registers, the result is stored back into the AC register. Similarly, if combination of Qn and Qn plus 1 gives you a result of 0, 1, then contents of AC register are added with the contents of BR register and the result is copied into the AC register. So once these operations have been performed, next we are going to perform an arithmetic shift right operation on the contents of AC and QR and then increment the sequence counter by 1. If your Qn and Qn plus 1 bits are either 0, 0 or 1, 1. It is not 1, 0 and it is not 0, 1. It is if it is a combination of both zeros or both ones. In that case, you need not have to perform any type of addition or subtraction operations on the contents of AC and BR. Directly, you can perform an arithmetic shift on the contents of AC and QR registers and decrement your sequence counter. So these are the four possible combinations of Qn and Qn plus 1. And once the sequence counter is decremented by 1, you again check the value of sequence counter. If until the sequence counter reaches 0, you are going to repeat the same process of checking Qn and Qn plus 1 and performing the operations. So if sequence counter doesn't reach 0, then you have to go back to the this particular step and again you start checking the values of Qn and Qn plus 1 and proceed with the remaining steps. If sequence counter reaches 0, then you have to stop the process. So this is how we are going to perform the multiplication operation on the two operands which are stored in BR and QR registers using Booth's algorithm. Now let us see an example of this particular flowchart by taking two values of BR and QR. So I want to multiply a 2's complement data where my contents of my BR register is -9 and the contents of my QR register is 13. So I want to multiply BR and QR. So when you are multiplying 2's complement data, as we have already discussed, when you are representing a negative number in a 2's, you have to when you want to perform an arithmetic operations on a negative number, in case of a 2's complement arithmetic, you have to convert the negative number into a 2's complement form and then perform an arithmetic operation on a particular number. So here I have two operands where the first operand is a negative value and the second operand is a positive value. So -9 is my first operand and 13 is my second operand. Coming to 13, you can use this multiplier as it is in your operation with the sign bit. Since it is a positive value, the sign bit represents 0, whereas your magnitude part of your data represents your binary representation of S13. But coming to a negative number which is -9, This is the binary representation of test9. Now you have to convert it into a 2's complement form. So for converting it into 2's complement form, I have to first convert it into a 1's complement and add 1 to it. So what is the 1's complement of 01001? It becomes 10110 and add 1 to it. So this is the 1's complement representation of my S9 and add 1 to it. It gives you 2's complement representation, which is 10111. So this is 2's complement representation of -9. Now, so and this is stored in a register BR, and similarly the next operand is stored in a register QR, and its binary equivalent is 01101. So according to your algorithm, your multiplicate is stored in a BR register and multiplier is stored in a QR register. So the next step is initializing the registers. So in the next step, I am going to initialize content of my AC register. So AC, as you know, it is a temporary register which is initialized to all zeros initially. And your Qn plus 1 bit, it is an extra flip flop that is initialized to 0. And similarly, the sequence counter SC is initialized to n, where n represents number of bits of your multiplier. So I am representing my multiplier with a 5-bit representation. So n becomes sequence counter becomes 5. So the next step, we have to take the representation of AC, QR, Qn plus 1 bit, and sequence counter. Now starting with this part of this algorithm, we have to start from here, taking values of Qn and Qn plus 1. So what is the content of AC? It is initially all zeros, and the content of QR is 01101, and Qn plus 1 is initialized to a value 0, and the sequence counter is initialized to 5. Right? So Qn is nothing but the least significant bit of your multiplier is represented as Qn. So the Qnth bit is 1. Now I will take the values of Qn and Qn plus 1. So what is the combination of Qn and Qn plus 1? So if you look at this, Qn is 1 and Qn plus 1 is 0. So it is a possibility, the combination is 1, 0. So whenever you are, according to your algorithm, whenever your combination of Qn and Qn plus 1 is 1, 0, you have to subtract contents of AC register and BR register. So since Qn and Qn plus 1 is a combination of 1, 0, I am going to subtract contents of AC and BR, which is done by means of AC plus BR complement plus 1. Right? So the contents of the AC register are all zeros and BR complement plus 1. So what is BR complement? Like, so BR complement is nothing but 01000 plus 1. It becomes 01001. Now add this value to contents of AC. So your value of AC becomes 01001 and QR is 01101 and Qn plus 1 is 0 and your sequence counter is 5. So after performing this operation, the next step you have to do is perform an arithmetic shift right on the content of AC and QR registers and decrement your sequence counter. So I have to perform an arithmetic shift right. So performing an arithmetic shift right is nothing but you have to shift the contents of your register towards your right, and in case of arithmetic shift, the most significant bit of AC register, so this will come in this particular position. Whereas for the next bit also you have to represent it by the same MSB bit of the AC register. And remaining bits you shift it towards your right. So it becomes 100 and this one will come here. So it becomes 10110 and Qnth bit will come in place of Qn plus 1. So it becomes 1 and decrement your sequence counter by 1. It becomes sequence counter is now 4. So what is the operation you have performed here? Arithmetic shift right on the contents of AC and BR and decrementing your sequence counter by 1. So this is one cycle. So now again check the value of sequence counter. The sequence counter is still not equal to 0. So we'll go for the next step. So in the next step, the loop continues. So we come back to the values of Qn and Qn plus 1. So now what is the value of Qn and Qn plus 1? It is, this is the value of Qn and 1 is the value of Qn plus 1. So the combination is 0, 1. So whenever the combination is 0, 1, according to the flowchart, you have to perform an addition operation on the contents of AC and BR. So AC is 00100, QR is 101110, Qn is 1 and the sequence counter is 4. So since Qn and Qn plus 1 is 0, 1, you have to perform an addition on the contents of AC plus BR. So my AC value is 00100 and BR value is, don't take BR complement, take just BR. 10111. Add them. So it becomes 11011. Next, the value of QR is 10110 and Qn plus 1 is 1 and sequence counter is 4. Now you have to perform an arithmetic shift right on the contents of AC and QR and decrement your sequence counter by 1. So perform an arithmetic shift right, it becomes 1 1 1 0 1 and this 1 will come in this place, so it becomes 11011 and your Qn plus 1 bit becomes 0 and the sequence counter is decremented by 1, now it becomes 3. Let's continue. So sequence counter is still not equal to 0, so we have to again check the values of Qn and Qn plus 1. So Qn is 1 and Qn plus 1 is 0, so it is 1 0. So we have to perform subtraction operation on the contents of AC and BR. So to the contents of AC, the value of BR is BR complement plus 1. It is 01001. So add them 10111. It becomes 10. So here have a carry of 1. You can neglect this carry. So QR is 11011 0 and your sequence counter is 3. Now the next step you have to perform an arithmetic shift right on AC and QR. So arithmetic shift right on the contents of AC and QR and decrement your sequence counter. So when I perform an arithmetic shift right, what happens? 0 0 0 1 1 0 1 1 0 1 and Qn plus 1 becomes 1 and the sequence counter is 2. So again the sequence counter is still not equal to 0. I have to again keep the value of Qn and Qn plus 1 where my Qn value is 1 and Qn plus 1 is 1. So it is a combination of 1 1. So look into the flow chart. Since it is 1 1, so whenever your combination is 1 1, Qn and Qn plus 1, you have to just perform an arithmetic shift right on the contents of AC and QR and decrement your sequence counter by 1. You need not have to perform any addition or a subtraction operation. So I'm just performing an arithmetic shift right. Becomes 00001 and this becomes 10110 and qn plus 1 becomes 1 and sequence counter becomes 1. So again the sequence counter is still not equal to 0. So we again check the values of qn and qn plus 1. So the qn plus 1 are now a combination of 0 1. So I have to add contents of AC and DR. 111, add them 10110 1 is qn plus 1. Here is 1 1. Here qn plus 1 is 0 1. So AC implies AC plus BR. Okay. Now arithmetic shift right on the contents of AC and QR and decrement the sequence counter. So after performing arithmetic shift right, it becomes 1 1 1 0 0 0 1 0 1 1 0 and your sequence counter reaches 0. So since your sequence counter reaches 0, so this is the end of your multiplication algorithm. So now like if you look at this result, the contents of AC register and QR register gives your product, which is a 10-bit product. You are taking a 5-bit multiplicand and a 5-bit multiplier. So you require two registers to store your product, which are stored in AC and QR. So whatever at the end of the process, whatever is the content of your AC and QR registers, that is your final product of your 2's complement multiplication algorithm. But here when you are performing a multiplication on a 2's complement data, after completing the process, if you get an MSK bit of 1, so out of your result. So if you look at the result, so sequence counter is equal to 0. So we stop the flowchart. Next, now look at the product. So this is your MSK bit of your product. So the product is stored in AC register and QR register. So when you look at the MSP bit is equals to 1. It means that this particular product is a negative number. So to get your actual product, you have to perform a 2's complement representation of this particular product to get the actual product. So what is the product which is stored in AC and QR? It is 111000101. I am combining and writing it down. Now perform a 2's complement. So what it means? Perform a 1's complement 000110100 plus 1. So it becomes 000111010. Okay. So this is equivalent to the decimal number 117. So you can put it down. So whenever your MSP of your product is the most significant bit is 1, in case of a multiplication algorithm, you have to perform a 2's complement of the result to get your actual product. And the sign bit remains the same. So the result is 117, but the sign of this particular multiplication operation remains the same 1. It means it is negative. So you have to represent the sign bit as negative minus, but when your MSP is 1, you have to convert it into a 2's complement form to get your actual product. So this is an example of 2's complement multiplication algorithm. call it as a Booth's algorithm. Thank you.